So chemical equilibrium, the content of the class will include concentration change during a chemical reaction. We will learn about dynamic equilibrium, and we also learn about the equilibrium constant. Then what we call Le Chatelier's principle, and then application of chemical equilibrium to Haber process. Haber process is the process where ammonia is produced in large quantity. And so without wasting of time, we'll go. Look at this graph. The graph here is talking about two different reactions, and that one of them is starting from a higher mass here, higher mass. So this one is decomposing from a higher mass. As it's decomposing, the mass is going down and down, 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 almost zero. So as time increases, the mass decreases. So as a chemical reaction occurs, the mass of the reaction will be decreasing because it will be gradually become used up. As the reaction progresses, the reactant decreases. So this graph is showing decrease in the concentration of reactant as time progresses. That is the first reaction. That is this one. It's showing. Okay. Then the second reaction is showing that as the reactant decreases, the product also increases. The product increases. So as the reactant decreases, the product is forming and is increasing. And as the two of them continues, a point will be reached called equilibrium point, where they meet. As the two graphs, they will meet somewhere. Where they meet, we call that place equilibrium point. Now, in this slide, you will see the word steeper there. There's a word being used there. This is steeper. The word steeper has to do with the fact that when the graph is steeper, it means the reaction is faster. When the graph is slopy, a slopy graph means the reaction is slow. When the graph is slopy, it means it's a slow reaction. Slow reaction. But a steepy graph, a steepy graph shows faster reaction, and very important in this class. So the steepy graph shows that the reaction is faster. The steeper the gradient or the steeper the graph, the faster the reaction. So the slopy the graph, the slower the reaction. So you must take note of that as well in this class. So that's about it. So when you see a graph that is like this is a slow reaction, and it's also kind of like this as a slow reaction. It takes a lot of time before it will reach equilibrium. But this graph here is steepy, means it's faster. So in an ordinary reaction, all reactants end up as product. There is a 100% conversion. That is ordinary reaction. But in many reactions, not all the reactant may be fully used up. And then we move to the slide. Okay, now let's look at it now. You see the reactants are faster at the beginning of the reaction. That's why it is steepy. Why is the graph steepy? this point, why is the graph steepy? The graph is steepy because the reactants are at a higher concentration. The graph is steepy because the reactants are at a higher concentration. That is why it is steepy. So it is faster. So the reactant are still not being used. So collision is very fast. So the reactant molecule collide faster. That is why it is steepy. So the steeper the graph or the gradient, the faster the reaction. And why is it steepy? It's steepy because there are plenty of reactants that are not yet reactant. So there is faster collision. They have more energy to collide, and you have collision occurs frequently. That is about that one. So as we progress in this thing, let's look at this one. The second scenario here, you see that the reactants are not too close. And because they are not too close, collision between the reactant will not occur frequently. So there will be the reaction will be slow and take some time. So the graph will be slopey. The graph will be slopey like before it gets used up to be slopey. Take time. So the collision rate here, it is slow. And you have heard of the word activation energy. Activation energy. Yeah, activation energy is the minimum amount of energy required for a chemical reaction to occur. It has a symbol of capital E, small letter A. The A is smaller. E is the energy. The word is actually energy. So to start a reaction, so this is the minimum amount of energy. This is the minimum, the smallest. This is the minimum amount of energy required for a reaction to start. It is usually 1 mark in your question paper. So when the molecules are farther apart, like in this case now, the molecules are far apart. Like here now, the molecules are far apart. It will take time for them to produce the minimum amount of energy required for effective collision. I'm not seeing you again. Where are you? Please on your video. That's very important.
You can't see me.
Okay, okay. All right, I'm seeing you now. So when the molecules are far apart, like we are just considering now, it will take some time for the molecule to produce that minimum amount of energy called EA, or activation energy, before the reaction can start. So when the molecules are far apart, they simply collide and then rebounds. So collision does not lead to chemical reaction until the collision finally brings, it is when they collide that they will have energy. So when they collide, the more they collide, the more they produce energy. So it takes some time for them to collide and get that energy. And that's why the reaction is
Sir. When
yeah,
you said this is the minimum amount of energy, what's that word?
required.
Oh, okay.
Minimum amount of energy required for a chemical reaction to occur. Required
Okay.
for a chemical reaction to occur. So now that is So when the molecules are far apart, if you take time before they can get the minimum amount of energy. So when the molecules are far apart, there are some features that we can bring out. What are the features that we can bring out here when the molecules are far apart? Now, when the molecules are far apart, this is the first feature is that collisions collision between the molecule, collision between the reactant. The reactant are unsuccessful.
So,
Yes.
so one thing I have to tell you is in my school, for my IGCSE, I'm not doing the exam like I'm not doing chemistry alone, biology alone. It's called coordinated science. That's what I'm doing.
Okay. So you will send me the syllabus, okay?
Yes, yes.
You
So
send,
while answering the coordinated science questions, we will skip to the chemistry questions.
so I can see the scope of coverage, please. You send,
Yes.
all
So
right.
I can, yeah, I'll send you all the questions and then you can cherry pick the chemistry questions out of them. They can start like learning with me in March.
Okay.
In March.
I understand what you are saying. So you make sure you send me the syllabus and the questions, and then we can go over it together.
Okay,
And
so
so,
I'll do that.
all right. So here, collision between when the particles are far apart, collision between the particles or the reactant are usually unsuccessful. Number two, when the particles are far apart, okay, it takes time. It or when they are far apart, the molecule do not have the EA,
Okay.
the reactant, the reactants do do not have the EA required required to start the reaction, to start the reaction. So when the particles are far apart, the first one, collisions are unsuccessful. Number two, the reactant particles do not have the EA to start the reaction. Number three,
You can remove number one. I'll finish with it.
okay, number three, collisions, number three, let me remember, okay. Number three, Number three, the frequency of collision is usually low.
Okay.
The frequency of frequency of collision, collision is usually low.
You can remove number two. I'm done.
Okay,
Yeah.
so that is the number three part of it. The frequency of collision is usually low. Therefore, the reaction is a slow reaction. So why is this slow reaction? Just tell them because collisions are not successful. Number two,
Okay.
the collision does not produce the minimum amount of energy. Number three, the frequency of collision is usually low. And finally, you can also write this one, number four, okay, a large, a large number, a large number of the reactants, a large number of reactants have energy, energy that is lesser than the EA required. required for a reaction to start. So that is the implication of when the particles are far apart. So there are 4 items. The 4 items will score you 3 marks.
Yeah.
The 4 items score you 3 marks, and you must know that. If you know that, you will be able to work harder. And when you work harder, you will be able to know how many points you are supposed to mention so that you can
To get your
score. So
marks.
it is usually 3 marks, but there are 4
Yeah.
points you must mention. Frequency of collision is low. A large number of the molecules do not have the energy called EA, or they have lower than EA. And also the molecule collision does not produce EA, and also the other one I have stated. So, but when the molecules are closer together, like the first one now, when the molecules are closer together, in this play, when they are very close, you will not talk about that collisions are usually successful. Collisions between reactants are usually successful.
Yeah.
Collision frequencies are high. Larger molecules have EA or more than EA. So let me give you that one as well. When
Yeah.
let me give you that one. So
You can erase everything. Yeah.
okay, so the first one, when they react, okay, when the molecules are closer in this one, closer molecule. So let's look at how it will look like. So in this case, number one, collision, collision.
Is this for wait, this is for when the reaction is fast.
Yes,
Okay.
yes. Okay. Between molecules are usually successful, usually successful. That's first one. Number two, um, large number of molecules, large number of the reactants, large number of reactants have EA or greater than EA for successful collision. They have large number of the molecules or reactants have EA or more than EA for successful collision. Number three, higher frequency of collision. There is higher frequency of collision, higher frequency of collision. And I gave you 4 the other time.
Yeah, you did.
Okay, can you remind me this which one I've not mentioned now?
So this is when you told me for when the reaction is slow, is
Yes.
a large number of the reactants have energy less than the EA
Okay.
required for a reaction to start.
Okay. And that one again?
Uh, the frequency of the collision is usually low.
Okay. And that one again?
The reactants do not have the EA required to start the reaction.
Okay. Then last one.
Collision between the reactants are unsuccessful.
Okay. So that is that. So it has been summarized together now. So these three,
Yeah.
so collision between molecules are usually successful. Large number
Yeah.
of the reactants have EA or more than E8 for collision. There's higher
Yeah.
frequency of, okay, then the last one now, the last one, um, collisions, collision between,
No, no, you can just erase everything there, but I'm already done writing it.
okay. So I
Yeah.
can move number one, Abi.
Yeah, you can erase, you see number 1, 2, 3, you can erase it and then write number 4 there.
Okay, all right.
Yeah.
So number four. All right. So number four, yeah. Collision between the reactants leads to chemical reaction. Therefore, the reaction is faster. Therefore, the reaction is faster. The reaction is faster. So that is the little explanation for when the reactants are higher and when the reactants are not higher in concentration.
Yeah.
If you're done writing it, let me know.
I'm done.
Okay, so we'll move on to the next slide.
Yeah.
All right, now I look at this graph again. Initially, there is no backward reaction. Back in the sense that the reactant collides and then you have your product. So as colliding, you have your product, A point will reach when the product themselves will also collide and form reactant back. So there will be a two-way reaction. So initially, there is no backward reaction, but as the product forms, it speeds up and provided the temperature remains constant, there will come a time when the backward and the forward reaction are equal and opposite. The reaction has reached an equilibrium. Now, in this case now, when two reactants collide, for example, you have A, reactant A colliding with reactant B, and then when they collide, they are getting reactant C as product. Now, when the C plus D as a product, C plus D as product, a time will come when the C and D, will also need to collide, because the C and D will be more than A and B. When the C and D is more than A and B, then they will also collide and go back to give you A and B. Why? Because they want the reaction to be balanced on both sides. The concentration and the product must be equal or balanced, call it constant. The concentration of the A plus B going to C and D must be equal to the concentration of C and D going to A and B. When
So
that
they have to be equal. So they have to be like equal to each other.
yes, equal. So this
Okay.
is very important. So you will see that there are two arrows. Therefore, in this topic, we'll be using an arrow like this to show forward reaction, an arrow like this to show backward reaction. So we have C plus D and then A plus B. So this arrow means reversible arrow. We call this arrow reversible arrow.
Reversible arrow.
Yes, so
Okay.
that arrow is different from this one.
Yeah.
And this one, they are different. They are different. So reversible reaction, all reversible reactions are represented by this half arrow. So the half arrow is key to our understanding of reversible reaction. So
Yeah.
as the reaction continues, the reactant becomes product, and product also goes back to form the forward reaction. So at that point, we say the reaction has attained equilibrium. The reaction has attained equilibrium. So when we ask you when did the reaction explain when does the reaction achieve equilibrium? So you now tell me it achieved equilibrium when the rate of forward, look at the word rate. It achieved equilibrium when the rate of forward reaction is equal to the rate of backward reaction. It achieved equilibrium. All right. When the rate of forward reaction is equal to the rate of backward reaction. That's when the reaction is at equilibrium. Explain how the reaction is at equilibrium. This occurs when the rate of forward, the word rate, you must mention it. The rate what rate must be mentioned when the rate of forward reaction is exactly equal to the rate of backward reaction. So that is very, very important to explain what does equilibrium mean. Equilibrium means that the rate of forward reaction is equal to the rate of backward reaction. So in that case, we have been able to explain the rate of forward of backward reaction. With that explained, you have demonstrated that you understand concept of chemical equilibrium. So that is how it should be. Okay. So is that can we move forward?
No.
Okay. So in chemical equilibrium, you will see in that graph that there are two types of graphs. There is one for broken line and there's one for unbroken line. You will discover that the one for broken line, they are the ones that shows that all the reactants have come to product. All the reactants have come to product. The one of unbroken line shows that not all the reactants have formed product. So under reversible reaction, not all reactants are converted to product, and not all products are converted to reactant. So, so it is like 50-50. It's like we can say that perhaps 50% of the reactant have gone to product, and also part of the product has come back to the reactant. So it is not 100% conversion. So you have the hypothetical graph. The broken line is different from the real line. The real one shows that not all, while the unbroken line is saying everything becomes product and all the product become reactant. You can see the broken line here getting to the end like this.
Yeah.
Showing that all have been used up. That is not true. In reversible reaction, not all the reactants are truly used up. Therefore, it is not reground. Look at it. So we have some remaining. We still have something like this remaining. From here to here, still remain. So not all the reactants. So for your objective, not all the reactants are used up. So not all the. Any question?
No, sir.
Okay, so let's move to the. So that's about that. So yeah. So in equilibrium, the forward reaction is equal to the backward reaction. So we have the arrow to represent that. There are what we call properties of a reaction at equilibrium. Properties of reaction at equilibrium. When we get there, we will talk about the property of the reaction at equilibrium. But let's look at this one. Important reminders. Important reminders. A reversible chemical reaction is in dynamic equilibrium or dynamic process. Everything may appear stationary, but the reactions are moving in both ways. Okay, that's one. Now, the position of equilibrium can be varied by changing certain conditions. So we have brought in another concept here. The concept we have brought in is the position of equilibrium. Position of equilibrium varies or can be changed by changing any of the following, by changing the concentration. We change the concentration, the position of equilibrium will change. We change the temperature, of the reaction, the position of equilibrium will change. If you change the pressure of the reaction, the position of equilibrium will change. And finally, if you change the catalyst also.
Okay.
Catalyst also will change the position of equilibrium. Catalyst. So these are the things that can affect the change in the position of equilibrium. There are two positions of equilibrium. There are two positions of equilibrium. The first one is the forward reaction. The second one is the backward reaction. So you have to determine where the equilibrium position is shifting to. So the word shift is very important. Shift. Shift means that there's a change in direction.
Yeah.
So is it shifting to the forward, to the right-hand side? If it shifts to the right-hand side, it means that the forward reaction is favored. If it shifts to the left-hand side, it means the backward reaction is favored. So there are some conditions that I will explain that will help us to understand all of that. Now, trying to get a down escalator gives, okay, that one is just an explanation. Now, what are the properties of a reaction system at equilibrium? Properties of a reaction system at equilibrium. There are four major properties, but I will only mention two. So, properties of a reaction system of a reaction in equilibrium. Number one, that is mandatory for your exam is that the forward reaction, the forward reaction, now the rate of the forward reaction, the rate of the forward reaction must be equal to the rate of the backward reaction.
Okay.
That is the first property of a system at equilibrium. The second mandatory property of a system at equilibrium is that the concentration of the reactant and the concentration of the product are a constant. They are in constant. The concentration of the reactant and the product are a constant at any temperature. So the ratio of the product to the reactant is a constant. So the concentration of the reaction of the reactant and the product is a constant. That one, you must know that constant. So we call it equilibrium constant. So the concentration of the reactant and product is a constant or a constant, anyone. So these two parties are easily, you must be able to understand these two. The remaining two, they are for your sixth form classes. When we get to sixth form, we will explain that you cannot easily get that.
But I'm in sixth form.
Yes, we're in sixth form. But let's take it little by little for your WAEC. Let's take it for now. You are just starting your sixth form. We are not going to equilibrium. So let's do the WAEC. IG equilibrium for now. Because if I mention the language now, for example, now, if I tell you that number 3 is the microscopic property, I will have to explain what are microscopic property of a reaction. Microscopic property. So the language is higher. So, but this one is your IG language, which you can really understand that the rate of the forward reaction must be equal to the rate of backward reaction, and also the concentration of the reactant and product is a constant. So that's the two major IG criteria for a system that is at equilibrium. So let's take the next slide, and then let's take the next slide. Let's look at the summary. When a chemical equilibrium is established, both the reactant and the product are present at all times. The equilibrium can be approached from either side. The reaction is dynamic. It involves forward and backward reaction. The concentration of reactant and product remain constant.
Sorry, I didn't finish writing it. Let me finish writing it.
Okay. So the summary of what we have discussed plus the other ones I have been mentioning before.
Yeah.
Both the reactant and the product present at all times. The one can be approached from either side. The reaction is dynamic. That is, it is moving forward and backward. Or you can say rate of forward reaction is equal to the rate of backward reaction. So when you are done, let me know.
Okay.
Okay. So now let's look at the next slide.
No. I'm on the last one.
Okay.
Okay, I'm done.
All right. So let's look at what is in the next slide that we can talk about now. Don't forget that
Okay.
we
Yeah.
have mentioned that the concentration of the reactant and product is a constant. So let's look at the next one. Simply put, if this one is what we call the Le Chatelier principle, the equilibrium law, Le Chatelier principle. If the concentration of all the substances present at equilibrium are raised to the power of a number of moles, they appear in the equation. The product of the concentration of the product is divided by the product of it. Okay, this is not equilibrium constant. This is not a the Chatelain principle. This is actually what we call equilibrium constant. Equilibrium constant. Okay. Now, equilibrium constant
Yeah.
is talking about the. Let me explain it in a way that is easier for us to understand. There are two types of
Yeah.
equilibrium. There are two types of equilibrium. Two types. The first one is the first equilibrium is the one in solution. Equilibrium in solution. Um, equilibrium in solution. What do you mean by that one?
Yeah.
What do you mean by equilibrium in solution? Equilibrium in solution means that
Equilibrium. Okay.
equilibrium, equilibrium in solution has a symbol of K, then subscript C. Then we also have
Oh,
gaseous,
okay.
we also have gaseous equilibrium. Gaseous, gaseous equilibrium. Gaseous equilibrium has to do with partial pressure. Gaseous equilibrium is connected closely to what? Partial pressure. Gaseous equilibrium has a link with partial pressure. Partial pressure. Partial pressure of gases. And therefore, the equilibrium from there is called Kp. The P there is partial pressure, while the C, the Kc here is the C there is concentration. That C is concentration at equilibrium. This P here, this P here is the pressure of the reaction at equilibrium. So C and P, they represent the same thing, but with different concepts. C there is talking about equilibrium concentration, and then P there is talking about partial pressure at equilibrium for gases. That is one. And then now, um, now we have Kc. Equilibrium value are expressed as concentration. That is for solution. Solution like you have maybe sodium hydroxide plus, okay, and that
Yeah.
so we have like have something like have something like equation that is in solution, like sodium hydroxide. Then you have to aqueous like this. Is in equilibrium with sodium hydroxide solid. This one. So
Yeah.
to write the Kc like this, we will say that the Kc is equal to the concentration of the product. This is the product, which is
Yeah.
sodium hydroxide like this. Capital bracket means equilibrium concentration. Capital bracket, capital bracket, capital bracket is equals to concentration. Concentration. And in equilibrium, we call it equilibrium concentration. So the Kc for aqueous reaction will be the concentration of sodium hydroxide to the power of a number of moles, A, over the concentration of sodium of the reactant, sodium hydroxide aqueous, to the power of the concentration, B. Now, let me use another example that will illustrate it very well. Another example that I want to use. Let me use another example like A plus B will give me C plus D. Now, A has a balance. So to balance A, I'll put small a. To balance B, I'll put small letter B. To balance C, I'll put small letter C. And then to balance the small d. So these are the coefficient of the reactant, and A, B, C, D. The small letter A, B, and C represent the coefficient. Therefore, to write
Okay.
Kc will be the product, the concentration of the product. So we have C capital bracket to the power of the number of mole like this times the second product D to the power of the number of mole like this over the
Okay.
reactant, the concentration of the reactant, the power of the number of mole over B constant, power of mole. So this is what we are saying in this. What is what the slide is talking about here? Everything here is what I was saying there. That if the concentration of all
Okay.
substances present at equilibrium are raised to the power of their number of moles, they are raised to the power of their number of moles. It's a number of moles, number of moles, number of moles, number of moles. They appear in the equation. The product of the concentration of the product divided by the product of the concentration of the reactant will give us our equilibrium constant. So in short, equilibrium constant is the ratio of the concentration of the product to the power of their number of moles to the concentration of the reactant raised to the power of their number of moles. So therefore, we can say that equilibrium constant Kc is equals to the ratio of the concentration
Right. That's the
of,
ratio of concentration.
yes, the ratio of the concentration of the product raised to the power of their moles, to the product, sorry, the ratio of the concentration of the product raised to the power of their mole and to the concentration of the reactant. The ratio of the concentration of the product raised to the power of the amount divided by the divided by the product of the concentration of the reactant raised to the power of their moles. So equilibrium concentration, what all this one was saying is the ratio of the concentration of the product raised to the power of their mole divided by the product of the concentration, divided by the product of the concentration of the reactant raised to or multiply. You can use the word multiply here. Multiply.
Yeah.
So here can you multiply? So that we make
Multiply.
Okay. So when you are done with it, let me know.
I'm not writing it down.
All right. So here you can use the word multiply. Okay. So that's about
Wait, divided by the multiply of the reaction.
Yes, multiplied by the function.
Yeah, understand. Okay.
Yes, multiplied by the concentration of the reactant raised to the power of their moles. So
yeah,
if you cannot, the formula can help to explain it very well. Formula is just that we divided product power of their mole over concentration, the power of their mole. Simple as that. That's that one.
Yeah.
So, like I said, are you still with me?
Yes, sir.
Okay, so, like I said, we have KC, we have KP. KC deals with solution, and KP deals with what? Pressure. And the pressure has to be converted to partial pressure. For example, if I have a mixture of gases, like I have gas A and then gas B and also gas C, mixture of gases, each of them have pressure. So if the pressure of gas A
This is for KP, right?
no, I'm not spoken. I'll talk about KC first, but I'm talking about KP now.
Yeah, I was asking. This is about KP.
Case, come again.
So we are doing KP right now. KP.
Okay, let's do KC first. I'm doing KP.
No. I didn't know KP. You just taught me KC. So now
Yes.
you're doing KP.
Yes.
Okay.
Yes, you're right. So I'm going to KP now. So now for KP, you will deal with a mixture of gases. A mixture of gases. So we have gas A, then gas B, and gas C. Each of these gases, they will have their amount. For example, if gas A is oxygen, that will be O2. Gas B is hydrogen, that will be H2. And gas C, maybe it's nitrogen, that will be N2. Now, if the mole of gas A is 15, let's say if the mass of gas A is 15 grams, the mass of gas B is 2.1 gram, 2.1 gram. The mass of gas C is 18 gram. you will convert these masses to mole first. So, number of mole of gas A. Before we left, we did mole, right?
Yes, yes, we did.
So you find the mole of gas A, and gas A is oxygen. So number of mole of gas A, the mass over molar mass. The mass is 15 divided by oxygen is O2. That should be 16 times 2, making it 32. Divide by 32. You
Yeah.
get the answer. Then number of mole of gas B will also be 2.1 over hydrogen is H2 and it's 1 times 2. That will be 2. So 2.1 over 2, get the answer. Then you calculate the number of mole of gas C is also 18 over N2, 14 times 2 is 18. So you have, sorry, that's 28. Wherever 28, so you get your answer. Now, if you do that, what will you get? Let's the first one, 15 over 32. 15 divided by 32, you will get
You get 0.47 more.
okay, 0.47. So here we have 0.47 more. And the other one, 2.1 over 2.
That'll be 1.05 more.
Okay, so 1.05. So 1.1. So we have 1.1 MOL, then 18 over 28.
Over 48.
That will be 0.64.
Is it not?
8.
Wouldn't it not be 18 over 28?
I look at it now. So I said 18 here, and N2 is 14 times 2, so 18 over 28, and that will give me 0.4. So we have here 0.64 MOL.
Yeah.
So after getting the mole now, you add the whole moles together. This is I'm teaching you AS now. I've only gone beyond your IG to AS now. So total mole.
You have to add them all together. Yeah.
The total mole will now be 0.47 plus 1.1 plus 0.64. You add it together. So
that'll be 2.16 more.
Okay. Plus 0.64. What did you get?
2.16 more.
Okay. 2.16. All right. So from this mole, you can calculate the partial pressure of each of the gas. So now to find the partial pressure, you will now tell me that there is something called mole fraction. Mole fraction. Mole fraction is like saying the mole fraction of oxygen now. The mole fraction of oxygen O2 will be the mole of oxygen, which is 0.47 over the total mole, 2.16 times the whole pressure times total pressure. So the mole fraction is simply 0.47 times 2.16. Sorry, 0.47 over 2.16. That gives you the mole fraction. Then to find
times 16.
No. If you multiply that times the total pressure, it becomes partial pressure. Ordinary 0.47 over 2.16 is your mole fraction.
Okay.
But if you now multiply by times total pressure of the reaction times total pressure, call it P total pressure, P total. we now have the partial pressure of the gas. That is P. The partial pressure of oxygen will now be the mole fraction times total pressure. See that? So it has some little step you must follow. So you calculate the partial pressure of oxygen, that which is 0.471, 2.16 times total pressure. You get the answer. Then you now come again and do partial pressure for hydrogen, which is 1.1 over 2.16 times total pressure. Get the answer. Then you now again calculate the partial pressure for nitrogen, which is 0.64 over 2.16 times total pressure. You get the three answer is what you will now use to calculate KP. It's what you use to calculate KP. So, but that is just a preamble. When we get to that place, we'll do that. It's like your AS chemistry. But now, let me go back to the IG level. Okay. So, let me go back to the IG level now. So, but we have learned something there. So let's look at this for an equilibrium reaction of the form A. I have done this one already. This one. A to small letter A, that A is the number of mole of A, and B to the number of mole of B, the reversible arrow there, to C to the number of mole of C, and so on and so forth. The equilibrium constant Kc is equal to the concentration of the product raised to the power of the mole is C, and then concentration of D to the power of D. D is the number of mole over the reactant. That is very important. Like I told you before, capital bracket is concentration or equilibrium concentration, while Kc is not equilibrium constant. So that's about this one. I have already explained that before. Now let's look at an example. Let's look at an example here. This example here. Example 1. Ion 3. Ion 3 as aqueous plus NCS minus. Okay, NCS minus aqueous to reversible arrow to give us ion 3 NCS2 plus aqueous. See, all of them are aqueous. All of them aqueous. That is a Kc. They will now ask you write the value of Kc. They write the formula for equilibrium constant. You will see that this one is to power 1. This one to power 1. Power 1. So therefore, Kc will be the product, and the product is this is the product, is FeNCS2 plus capital bracket 1 over the reactant Fe3 plus capital bracket power 1 and NCS minus capital bracket power 1. When it is power 1, we don't show it. We don't put the 1 there because 1 times the concentration will remain the same thing. It does not change. So when it is raised to power 1, we do not show it in the formula. Then the next thing we do is to find the unit. So you must add your unit to it. So in what unit? The product is mole per dm cube. The product is mole per dm cube. There are two reactants. The reactant for ion 3 is also in mole per dm cube. Mole per dm cube. Second reactant, NCS, is also in mole per dm cube. So mole per dm cube can cut mole per dm cube. So let's do that. So this one can cut this one. So what we're having there is 1 over mole per dm cube. So let's make it normal, no fraction. So per dm cube will become dm cube, not pi again. If the mole comes up, become per mole. So mole minus 1, then
O minus 1.
dm cube like this, but it's now on straight line.
Yeah.
So that is it.
Oh, okay.
And so that's how they got this answer they got here. This answer.
Okay.
So this answer they
Okay.
got here. Is it clear that this answer? That's how they
Yes,
got the
sir.
answer. So
Yeah.
dmq per mole. So whenever you write the formula of Kc, you must always put the unit by writing. If it is square, you put square. Square means times 2. That is about that. So
Yeah.
okay, so we'll move on to the next slide. Let's look at another that slide now. Okay, well, dealing with the value here, the value of Kc. There's only one factor among the one I gave you, like concentration, temperature, pressure,
Yeah.
and catalyst.
Oh, yeah.
The only one
Yeah.
that
Let me
can,
write it down.
yes, the only one that can
There's
affect the
no,
value.
yeah.
What?
No, sorry. Sorry, continue.
Okay. Now there are 4 factors that I mentioned before. I mentioned temperature. I have mentioned temperature. So I'll mention it again now. So I have mentioned temperature, temperature. That's first factor. Number 2, pressure. Pressure. Number 3, concentration. Concentration. Number 4, catalyst. Out of these 4 factors, only one that affects the value of the equilibrium constant Kc. Only one. And the only one that can affect is your temperature. If you change in temperature, we change the value of Kc. But change in pressure, change in concentration, and catalyst does not affect the value of Kc. It's only temperature that can change the value of Kc. So temperature, concentration change, pressure change, catalyst change has no effect on the value of Kc. So you must take that in your question. All right. So
Okay.
all right. So we'll move on to the next slide. So
Yeah.
okay, the next slide is talking about the another a law, or we call it principle of chemical equilibrium. You must know this one. Now, let me explain the principle of chemical equilibrium called Le Chatelier's principle. It simply states that when a change is applied to a system, what do you mean by system? A system is a chemical reaction. So a chemical reaction is equal to a system. So when there's a change in a chemical reaction that is in a dynamic equilibrium, what do you mean by dynamic equilibrium? Dynamic equilibrium means that rate of forward reaction is equal to the rate of backward reaction. So when there's a change, when a change is applied to a system in dynamic equilibrium, the system readily react in such a way to oppose the effect of the change. The system react or adjust itself to remove the effect of the change. It goes against the change. For example, now, if you increase concentration of the reactant, the system will adjust itself and give you more product. See that it will annul or it will oppose it. It will oppose the effect. So if you increase the product, the system will adjust itself and give you more reactant. If you increase, so if you increase the temperature of the reaction, the system will adjust itself and then make more product or decompose and make less reactant. and make more reactant. So if you change the factor of temperature, pressure, catalyst, and concentration, the system has a way to adjust itself to annul or to oppose the effect of the change. So it's a principle, not a law, as it were. So they call it Le Chatelier principle, after the man that observe and develop the idea. So when a change is applied to a system in dynamic equilibrium, some things here are constant that you must note about. When a change, is when a change is applied to a system in dynamic equilibrium, that is one mark. So that's one mark.
Okay.
What happened? The system reacts in such a way to oppose the effect of the change, one mark. See that in A level, it is either 2 or 0. There's not like one mark. You must get the whole thing right. So it is 2 marks at once. So, but it's possible they can also give you one mark, but don't bank on that one. Ensure you know it completely. You know it completely, it will help you a lot. So when a system is at equilibrium, is at dynamic equilibrium, and there's a change, the system will react to oppose the effect of the change. Simple as that. When a change is at the system, the system will react to annul or oppose the effect of change. So you must know that. So everyday example, a rose bush grows with increased vigor after it has been pruned. Okay, that's another one. Let's look at chemistry example. If you do something to a reaction that is in a state of equilibrium, the system position will change to oppose what you have just done, just told you now. So if you add more acid to a reaction, the reaction will react faster than before because it becomes more concentrated, so it will be faster reaction. So that's the law. So let's go to the next one, and then we'll apply the law. Okay. So we'll apply the law when the time comes. So the law is given for us to apply it. So application here is very
done.
Okay.
I'm done. I'm done.
Okay, we are done, right?
Okay. Yeah.
Okay. You are done, Abi?
Yes, sir.
Okay. Now, let's look at the first factor that affects the position of equilibrium. The first factor is concentration. So we want to examine how concentration affects equilibrium. Now, it is very simple. When you increase concentration, the position of equilibrium changes, or goes to the right-hand side. The position of equilibrium moves to the right-hand side or favors the right-hand side. Why? There are more reactants. So the reactant will react and give you product. So the position of equilibrium shifts to the side of the product. That'll be one mark. So whenever you increase concentration at a constant temperature, the position of equilibrium moves to the right-hand side. Similarly, if you increase the concentration of the product, the position of equilibrium will shift to the side of the reactant, and there will be more reactant produced. That is the two things there. Let us do it again. If you increase the concentration of the reactant, the position of equilibrium shifts to the side of the product. So there will be more of the product produced than the reactant. So the concentration of the product will increase until equilibrium is achieved. If equilibrium is not achieved, the concentration of the product will continue to increase until equilibrium is restored. So it is doing something opposite. Also, if you increase the concentration of the product, the position of the equilibrium will shift the side of the reactant. So there will be more reactant compared to the product. Now, the concentration of the reactant will continue to increase until equilibrium position is restored. That is what is called a concentration as it affects the position of equilibrium. That's about that. Is it clear?
Yes, sir.
Mm.
But no. Let me quickly write the paragraph that we're just talking about. If you increase the concentration, so let me just quickly write it down.
So don't forget that Kc does not change. They are saying that it can change theoretically, it remain constant. Only temperature that can change it. So it remain constant because if you increase concentration, the reactant react and give you more product to restore the value of Kc to make Kc constant. So once you increase the reactant will react and give more product and make the whole thing constant, so it does not affect it. So let's look at the next slide.
No, I'm not done.
Okay.
No. Okay, so I'm done.
All right. So we'll move on to the next slide. Let's see what's the next slide. Now, in the next slide, you can see that a reaction is being given to us there. The reaction is that of organic reactant and organic product. Here we have ethanol. This is ethanol. Ethanol reacting with ethanoic acid. Ethanoic acid reversibly giving us ethyl ethanoid. So we have not done organic chemistry. Ethyl ethanoate plus water. Okay, so we have the reactant, we have the product. Ethanol reacting with ethanoic acid, reversibly producing ethyl ethanoid and water. This reaction is never 100%. Not all the ethanol and ethanoic acid will form ethyl ethanoid and water. And not all the ethyl ethanoid that will form the ethanol and ethanoic acid. So it is like half-half. So that's about that. Now we are required to write the equilibrium constant. This was at just ratio 1:1. Now they are telling us that the ratio of the product, that is this one, the product are CH3COO C25. times H2O over the reactant CH3CH2OH times CH3COH is equals to 4 at this temperature. This value 4 depends on this temperature. If this temperature increases, the value of 4 will change. If you increase it, the 4 will increase. If you decrease it, the 4 will decrease. So it's temperature. The value is temperature dependent. Right. Now let's look at what is there again. If I move the slide forward. Okay. Now let's look at increasing the concentration of ethanol. Ethanol is a reactant. It's a reactant. So you increase the concentration of the reactant. What happens? The reactant will react and produce more product. Therefore, yes.
No, nothing. I'm saying yeah.
Okay. So the reactant will react and produce more product, making sure that the position of the equilibrium shifts to the right-hand side. So are going to be having more of CH3, COO, C2H5, and water until a Kc value becomes constant, becomes 4 again. Because the product over the reactant will give you 4. Therefore, when you increase the amount of the reactant, it will react and give you this one. And when you do this one, the ratio of the product to the reactant to the power of the number of mole will be calculated and you get your 4 back. So Kc remain unchanged. Okay, so, but what are we learning here is that when you increase the concentration of the reactant, the position of equilibrium will change, will move to the right-hand side. More of the product will be formed until equilibrium is restored. That's what we are looking for here. So increase in the concentration of any of the reactant. It can be ethanol, it can be ethanoic acid, any one. Once you increase one, the two of them are no longer equal. So one that has increased, they will react, and when they react, they will produce more product. So it favors forward reaction. The same thing goes with the product. If you increase the concentration of the product, to favor the backward reaction. That is about that. So let's see the next slide. Okay. Are you writing it?
Yeah.
Okay.
I'm done.
Okay. So let's look at, so let's move to the next slide. All right. Now let's look at the other one, which is water. Water here is a product. We are decreasing the concentration of water. So how does it affect the position of the equilibrium? Where will it move to? Now I want to take it to another level now. Look at the water in the equation. It's on the right-hand side. That's your product. To decrease it means to remove some water. Are you following? To decrease it means to do what? Remove some water. You are removing
to remove some water.
Some water molecule. Some water molecule. The meaning of that is that there will be more space in the product. There will be lesser product. We are removing part of the product. So as you remove part of the product, the concentration of the product will decrease. As the water is being removed, the amount of the product becomes smaller compared to the reactant. So when that one happens, the reactant will react and produce more water. The reactant will now react and add more water to replace what was removed. Therefore, the position of equilibrium goes to the right-hand side to compensate the removal of water. The reactant will produce more water to replace the lost water until equilibrium is finally restored. So Kc will remain constant. So as you remove the water, the reactant will react to produce more water. Position of equilibrium shift to your right hand side, and it will continue to shift until the value of Kc is restored. Is that clear?
Yes, sir. So you
Okay.
have to shift right outside for it to be restored.
Okay.
Okay, you can change it.
All right. So we'll move on to the next slide.
Yeah.
Okay. Now I am in the next. Let's look at the summary for equilibrium. If you increase the reactant, equilibrium position move to the right hand side. If you decrease, the reactant, if the reactant decrease, the product will react to replace the reactant. It will react and produce the reactant. So equilibrium position will shift to the left hand side. If you increase the concentration of the product, there will be more product than the reactant. So the product will react to produce the reactant. So it will shift to the left. Similarly, if you increase the concentration of the product, if you decrease the product, there will be more reactant than product. So the reactant will react to replace the product you have produced. Therefore, equilibrium will shift to the right hand side. So this four, you will see in this one, we're talking about increase and decrease. Increase and decrease. So you must get used to that. So when you increase, let's now learn it very well, because this is the important aspect. If you increase the concentration of the reactant, position of equilibrium shift to the right hand side. That's one. If you increase the concentration of the product, position of equilibrium shift to the left hand side. So that is increase. Now, if you decrease the concentration of the reactant, if you remove away the reactant, so there will be lesser reactant compared to product. So the product will react and replace the reactant removed. So position of equilibrium shift to the left hand side for the reactant. If you decrease the concentration of the product, there will be more reactant than product. So the reactant will react to replace the product. So as they react to replace the product, position of equilibrium shift to the right hand side. So these four items must be in your brain. Any question?
I'm writing it down. I'm writing it down now.
Okay.
Okay, I'm done.
All right. So we'll move on to the next slide.
So how many
Look at
slides are there?
okay. Let's
So how
look
many slides are there?
no, we will not finish this thing today, but we have done with concentration, then we now go to the one of pressure. Okay, but we are done with the
Sir, sir,
yeah.
sir, is the Haber process? Is
Okay.
the Haber process? Is it? Is it under? Oh, sorry. The Haber process. It's
Yes.
under. Um,
Under chemical equilibrium.
reversible reactions and equilibrium. Yeah.
Yes. About process, you
Okay.
get it under equilibrium because under application of chemical equilibrium. That's how you learn it. Okay.
I was studying it by myself.
Okay. Okay.
So
That's great. So
so
let's
we'll be doing that. So okay. No, it's fine. Sorry.
okay. So let's look at this one. SO2 plus O2 gas to give us 2SO3. They now ask us, predict the effect of increasing the concentration of oxygen on the position of equilibrium. If we increase oxygen, what will happen?
If you increase what? Sorry, sir.
Well, if we increase the concentration of oxygen, where will the equilibrium go to? Is it the right or is it the side of the reactant or side of the
If
product?
you increase it, it will move to the right.
Move to the right. Okay, that's correct. So we will now write position of equilibrium shift to the right hand side to restore the value of Kc. So the amount in mole of SO3 will increase until Kc is restored. Second one, predict the effect of decreasing the concentration of SO3. If you decrease the concentration of SO3, what happens to the position of
If you
equilibrium?
concentration to move to the right.
Yes, because we are removing some of the SO3, so it will be lesser. So the reactant will react and then produce more SO3. This is just knowing the where it will move to. Later, you will be explaining what I'm explaining now.
Yeah.
So that is about that. So we are correct with that. Now let's look at pressure. We are going to start. We are going to summarize here. I will just talk this pressure. We stop here so that how many times are we having the class? Is it once a week or twice?
Um, I think it's I think it's once every I think it's twice a week because we might be having class on weekends. But you should ask my dad. My dad will tell you.
Yes, I think before I was telling you that today and Saturday. So Saturday I will arrange myself since your time is ahead of us by 1 hour. Is it 1 hour?
Yep.
So
Yeah.
this is 7 o'clock now. So you are also 8 o'clock, Abi. So what we
Yes, I'm at 8 o'clock right now.
okay, what we do is that on Saturday we'll start around 8 in the morning, and my own 8 is your own 9. So because
Yeah.
I'll be having class by 10, so we start around 8, finish around 10. So
Okay.
so let us stop here. Well, pressure is on its own scale. But here, let me just write for pressure that pressure Kp like this. For example, if I have 2SO2, let me write it this way. Okay, if I have A plus B to give me C plus D, and I have here A, I have small b, I have small c, I have D. My Kp here my Kp here will be equals to the partial pressure like this. Partial pressure in slanting form. In slanting form, then I'll now put in bracket like this. In bracket like this, small bracket, not capital bracket, C like this. Then I'll now put C like this, the power of C times partial pressure of D like this, the power of D over partial pressure of the reactant A in bracket, the small letter A times the partial pressure of B, the power of B. This is the formula for calculating equilibrium concentration for pressure. All right, but now by next week, by Saturday, we'll deal with this one very well, because it has its own pathway of dealing with pressure. So pressure deals with moles. So the moles are very important. Now, if the mole of the reactant are higher, forward reaction. If the mole of the reactant are lower, backward reaction. That's how it is. Very simple. Moles of the reactant are higher, forward reaction. Mole of the reactant are lesser, backward reaction. So also, if the mole of the product are higher to backward reaction, the mole of the product are lesser, forward reaction. It's very simple, but that would be so. I mean, Saturday. So let us stop here. Okay. Yeah, so that I will send you the video of what we are doing today, and then you can go over it.
I'll send you 5 years of theory and multiple choice past questions.
Okay.
Like, yeah, for coordinator science.
Okay, good. I want to hear that for coordinator science.
And then you pick out, and then the chemistry questions in it, you pick them out and they ask.
Okay. All right. Great.
Yeah, I need your email.
All right.
In chat. Yeah, in chat.
So it's nice having you this evening.
Same. Right.
So enjoy yourself.
Yeah, you too, sir.
Yeah, take care. So I will get the video ready and you have it.
Could you send an email? Could you send an email to your email? Could you send it to my dad?
It's already on that WhatsApp. The email.
Oh, okay. Yeah. Okay. Okay.
Take care. Bye-bye.
Thank you, sir. Bye.